Hi, Kim here. Today we're going to be talking about the difference between structural, molecular, and empirical formulas when we are identifying and describing chemical compounds. We're also going to be learning how to take a structural formula and determine the molecular formula of a compound, and then to go from the molecular formula to the empirical formula. Let's get to it. Our learning goals for this video are going to be to explain the difference between structural, molecular, and empirical formulas. You're going to be given the structural formula of a compound and asked to determine the molecular formula of the compound. And then, given the molecular formula of the compound, you're going to determine the empirical formula of the compound. We'll end by doing some practice questions, switching between the formulas. You should have something to write with and something to write on before we get going. A structural formula is a formula that shows the arrangement of atoms relative to one another in space. Some examples of structural formulas that you're used to seeing are ball and stick models and Lewis structures of compounds. The molecular formula shows the actual number of atoms of each element in a particular compound. And the empirical formula shows the simplest whole number ratio of elements in a compound. We're going to take a look at a couple of examples, so get ready to write these down so that you can start to make connections between these three types of formulas and how they each can be useful given the context. We'll start with an example of a molecule called ethane. Ethane has a structural formula that looks like that drawing there. There's two carbon atoms connected to each other with a single bond, and each carbon atom is single bonded to 3 hydrogen atoms. So the structural formula is literally the Lewis structure of that particular compound. I can count how many atoms of each element are in that structural formula. I see that there are 2 carbon atoms and 6 hydrogen atoms. That allows me to then go ahead and write my molecular formula. There are 2 carbon atoms, so I'm going to write C and then 2 as the subscript after the C, H and then 6 as the subscript after the H. Notice that because C and H are chemically bonded to each other, this is one molecule that is all bonded together. I am writing this chemical formula almost like it was one word. There's no spaces between the C and the H, there's no plus signs, right? And the numbers are subscripts to represent that this is how many atoms of each element there are in that one molecule. Now, to go from the molecular to the empirical formula, I want to see if that ratio can be reduced at all. So the ratio is 2 to 6, 2 carbon atoms to 6 hydrogen atoms. And I want to figure out, is there a number that both 2 and 6 are divisible by? So I can reduce the ratio. It turns out that both 2 and 6 are divisible by 2. So 2 divided by 2 is 1, and 6 divided by 2 is 3. So I can simplify this ratio from 2 to 6 to 1 to 3. And I can write the empirical formula as CH3 or C1H3. This is the reduced form of the molecular formula. I've reduced that ratio to show the simplest ratio of the 2 elements that are in the molecule. The structural and the molecular formulas are both showing me how many atoms of each element are actually in one molecule, and the empirical formula is showing me the simplest ratio of the elements in that molecule. Let's look at a second example. Let's look at methane. I like methane as an example because you'll see that sometimes empirical formulas and molecular formulas end up being the same. So methane's structural formula is that it is 1 carbon atom single bonded to 4 hydrogen atoms. So its molecular formula is CH4 or C1H4, but you rarely see the 1 written down. That ratio can't be simplified anymore. 1 to 4 is already as simple as that ratio is going to get. So the empirical formula is the same as the molecular formula for this compound. The molecular formula for methane is CH4 because that's what the one molecule looks like. The empirical formula for CH4 is also CH4 because that ratio cannot be further reduced than it already is. Let's try a third example, ethene. Ethene is C2H4 as its molecular formula. I can take a look at the structural formula and see that there are 2 carbon atoms double bonded together, and then each carbon atom is single bonded to 2 hydrogen atoms. So there's 2 carbon atoms in the molecule and 4 hydrogen atoms. So just counting the number of atoms of each element for my molecular formula, that's C2H4. That is a 2 to 4 ratio, and both 2 and 4 are divisible by 2. 2 divided by 2 is 1, 4 divided by 2 is 2, so I end up with a 1 to 2 ratio of carbon to hydrogen, whereas I had a 2 to 4 ratio of carbon to hydrogen before it was simplified. So my molecular formula is C2H4. My more simplified empirical formula is C1H2, or just CH2. Propane is 3 carbons single bonded to each other in a chain, and then each of the end carbons are bonded to 3 hydrogens, and the carbon in the middle is single bonded to 2 hydrogens. That's the structural formula. So I count 3 carbon atoms and 8 hydrogen atoms, meaning my molecular formula will be C3H8. So let's think, C3H8, a 3 to 8 ratio. Can that be simplified anymore using whole numbers? It can't. 3 to 8 is already as simplified as we can get. If that was a fraction, right, 3 over 8, it couldn't be reduced any further. So my empirical formula is also going to be C3H8. So my molecular formula and my empirical formula are the same for propane. Now it's time to do some practice. You've seen 9 structural formulas below. For each structural formula, take the time to determine the molecular formula and, if it's different from the molecular formula, the empirical formula for each compound below. Pause the video because I will start going over the answers in 3, 2, 1. For number 1, I count 3 carbons and 7 hydrogens. That is a 3 to 7 ratio, which can't be simplified any further. So I would write the empirical formula the same as the molecular formula, C3H7, because that ratio cannot be simplified. The next question, question number 2, I count 3 carbons and 6 hydrogens. That is a 3 to 6 ratio, which can be simplified because both of those values are divisible by 3. So 3 divided by 3 is 1, 6 divided by 3 is 2, so my ratio reduces to C1H2 for my empirical formula. For number 3, I count 2 carbons, 6 hydrogens, and 2 oxygens. This ratio is 2 to 6 to 2, carbon to hydrogen to oxygen. Each of these values is divisible by 2, so 2 divided by 2 is 1, 6 divided by 2 is 3, 2 divided by 2 is 1. I end up with a 1 to 3 to 1 simplified ratio of C1H3O1, or CH3O as my empirical formula. For number 4, I count 4 carbon atoms and 8 hydrogen atoms. That is a 4 to 8 ratio, and so since both of those numbers are divisible by 4, I can get a simplified formula, empirical formula of C1H2, or just CH2. For number 5, I count 2 carbon atoms, 6 hydrogen atoms, and 1 oxygen atom. Because there is 1 oxygen atom, this ratio cannot be simplified any further, and the empirical formula will be the same as the molecular formula. Number 6, just like with number 4, I count 4 carbon atoms and 8 hydrogen atoms. So it seems like these 2 compounds, number 4 and number 6 here, have different structural formulas, but the same molecular formula. Interesting. This is again a ratio of 4 to 8, so just like the answer for number 4, we end up with an empirical formula of CH2 again. Finally, we have number 7, C2H2, a 2 to 2 ratio can simplify to a 1 to 1 ratio, so we end up with an empirical formula of C1H1, or just CH. Number 8, there are 6 carbon atoms and 12 hydrogen atoms, so both 6 and 12 are divisible by 6. We end up with a 1 to 2 ratio. 6 divided by 6 is 1, 12 divided by 6 is 2. So the empirical formula for C6H12 would be CH2. And finally, C6H6, just like a 2 to 2 ratio, this is a 1 to 1 ratio as well, 6 to 6. And I end up with the empirical formula of C1H1, or CH. Awesome job today. Let's review our learning goals. Make sure we feel confident going between structural formulas, molecular formulas, and empirical formulas after watching this video. Way to go.